Hi, welcome back to day 2 of partial derivatives. If we're trying to take the derivative with multiple variables, the issue is what are we taking the derivative with respect to? Since we typically take the derivative with respect to x and y, we're going to continue with that same concept. Now the formal definition is one we use with the traditional definition. That's our limit definition right here. And we've adapted this to multiple variables. So we saw this yesterday in our video, where if we're taking the derivative with respect to x, we're only looking at how x changes, where y is constant, where y is a constant value for us. Over here, if we're taking the derivative with respect to y, our x value is the constant, and we're looking how the function changes as y changes. In short, when we take the derivative with respect to a requested variable, we're going to treat all variables as constants. So let's take a look at some examples. For question number 1, we're given the function f of x, y, 2x cubed y squared minus 7x squared y. Right here. So when we take this derivative with respect to x, we're going to treat y as a constant. Now, we say the phrase partial derivative, but we've always really done partial derivatives. It's just that last year, like if we were given a function calculus 1 in single variable calculus, like if f of x equals x squared, we're looking at a single variable. The derivative would just be 2x. The thing is that there's no other derivative right there. And so this tells us how the function is changing only in terms of x. But with partial derivatives, it's the same thing. For this example, I'm still looking at how the derivative of the function changes only with respect to x. So I can treat y like a constant. And that's the same thing like right here. If I have like x squared plus 3, well, the derivative of x squared is 2x. Well, the derivative of 3, which is not an x, becomes 0. So we don't have to worry about the 3. The same thing is true for anything that is not an x in this problem right here. So when we take the derivative, when we look at the x, we have x cubed. When I take my derivative using my power rule, we will get 6x squared. We leave this as y squared like it's a constant. Minus, take the derivative over here with respect to x, the power is 1, so that becomes 7, the x goes away, and we're left with y cubed. And there we have it. Now remember, another way we could write this is using that other notation, the partial of f with respect to x. And this symbol here, remember, is a del. It was one of our symbols for a del, and it's talking about a change, sometimes called little d, right, like a little cursive d right there for changing the function with respect to x. So let's take the derivative with respect to y now. So in this case, the x cubed is a constant. So I look at the y squared, we're going to drop our power to the front, and we would get 4x cubed y minus, take the derivative here with respect to y, we drop our 3 down to the front, we get 21, the x is just like a constant, and we get y squared. And there's our derivative with respect to y. Alright, so let's try another one right here. Now this is going to look a little uglier, but when we take the derivative with respect to x, it's really not that bad, because the only function here with an x in it is the x to the 4th. So its derivative would be 4x cubed. Well, what happens to the 6y? Well, I'm only looking at how the x values are changing in this problem. So we don't care about the y. It's a constant. So everything else just goes to 0. So there's our answer. Likewise, when we're taking the derivative with respect to y, now I only have to worry about the 6 root y. So the x to the 4th becomes 0. And when we take the derivative of 6 root y, that becomes 6 over 2 root y. You can leave it like this, or 3 over root y. Now, if you forgot how quickly we can get the square root of y, remember that's y to the 1/2. So that's 1 over 2 y to the 1/2 when you take the derivative. So let's try h. Oh no, s and t. So we're going to take the derivative with respect to s. Now I know what y'all thinking, Mr. Warnow, shouldn't that be an h? I can't spell very well, so I left it as an f. So I'm sorry about that. So when we're taking the derivative only with respect to s, I only have to look at this one, this term, and the last term. Because that has no s in it, it just goes to 0. So when we take the derivative, we're still going to be left with this t to the 7th. And taking the derivative natural log becomes 1 over s squared times the derivative of the inside, 2s. And again, this becomes 0. Oh, this one's a little bit nasty, so I'll rewrite this as s to the 4/7. So we're going to get minus 4 over 7s, subtract 1, negative 3/7. And you can leave it like this, but it cleans up pretty nicely. Here we're going to get 2t to the 7th over s, because the s's are going to cancel, minus 4 over 7s to the 3/7. And leave it alone, right there. Taking the derivative with respect to t, okay, that's not too bad. Again, I don't worry about the natural log part here because that doesn't have a t on it. So we would get 7t to the 6th. We're going to keep the natural log the same. Now I still need the natural log because it's like my constant. Like if this was 5t to the 7th, right, we would get 5 times 7t to the 6th. That's kind of what we did here, except the 5 here is our natural log. Plus, this is a little bit tougher. That's 9t to the negative 3. So that becomes minus 27t, subtract 1, negative 4. And I could write that as 7t to the 6th, natural log s squared minus 27 over t to the 4th. Leave it alone. Don't fix it. You can want to write it as a single fraction, I guess. I suppose you can. Right there. Very easy to do. All right, so let's take a look at another one right here. Let's go ahead and look at another example. Give me a second. So for question number 4, well, okay, this escalated quickly. Okay, so we are taking the derivative with respect to x. This one looks a little bit worse because we are going to have to use our product rule. So let me go ahead and zoom in here. This is cosine 4 over x, x to the 2nd, y minus 5y cubed. I am going to have to use the product rule here, so this is going to get nasty fast. So we're going to write out the first, cosine 4 over x times the derivative of e. Well, that's just e to the x squared y minus 5y cubed times chain rule the derivative of the inside with respect to x. That just becomes 2xy minus 0 because that has no x to it. Plus the second, e to the x squared y minus 5y cubed times the derivative of the first, chain rule, negative sign 4 over x times the derivative of the inside. This is just 4x to the negative 1 becomes negative 4 over x squared. Okay, I am not going to worry about cleaning that up at all. I am just going to leave it alone. And there's our derivative with our product rule. Ew. It's about as bad as I get right there. So let's take the derivative with respect to y. Now what's nice about this one, there is no product rule here. Be very careful. I don't have to use the product rule here because my first function is in terms of x. So I can just leave that alone. So it's like if I said 5e to the x, it's just going to be, or e to the x squared, it's going to be 5. Leave it alone, and I take the derivative e to the x squared times 2x, okay? So I can leave this constant alone. That cosine x 4 over x is a constant. But now when we take the derivative of our e function, the derivative of e is always itself e to the x squared y minus 5y cubed times the derivative of the inside. Now we got our chain rule part here. We do have a chain rule. So the derivative with respect to y just becomes x squared minus 15 y squared. And there is our derivative. All right, if you go to part 2, we're going to take a look at a couple more equations, a couple more examples. I'll see you then. Bye-bye.